conduction is a little more challenging than what we did before, right? So you might remember that conduction is the transfer of heat through air. Remember, conduction is heat transferred through a what? Solid, right? Through a solid, right? Convection is through a what? Through a fluid. And radiation is heat transfer via EM radiation through a gas as well, but also through a vacuum. Yeah. Right? So the transfer of heat from one point to the next. Conduction, that's what we're focusing on today. Conduction is the heat flow through a solid. Convection is through a fluid. Radiation is through a vacuum. Right? Or fluid, or gas, sorry, via electromagnetic radiation. So we are going to focus on solids. Right? There's a small diagram here that's got the block. Right, let us run through this. Conduction is the process by which heat flows from a hotter region of a substance to a colder region without there being any net movement of the substance itself. So the substance itself doesn't move like in convection. All the particles themselves move, right? But here, the particles don't move. What does happen to them? What does it do in conduction? During conduction, what does happen to the gas? I mean to the solid particles? They vibrate and they transfer the energy, right? Right, mechanisms of thermal conduction. All this in your handout, right? We just want the important stuff, right? The kinetic energies of molecules in a substance directly related to temperature, right? Anybody remember how they're related? Kinetic energy and temperature. How are they related? Directly or inversely? Directly, right? If you increase temperature, you will increase kinetic energy, right? We are going to prove this later on. So Monday, right? We are actually going to prove this relationship here. Kinetic energy equals something, right? I'll keep it a secret for now. Right, in metals, there are mobile electrons that transfer energy throughout the entire lattice. The mobile electrons in the metal move thousands of times faster than that of gas and liquids. And as a result, the thermal conductivities of a metal are much higher than that of liquids. So we know that, right? Metals are better conductors. And the main reason is because of the mobile electrons, how fast they can travel through this solid. All right? So you might see a next word pop up there that's very important. Thermal conductivities. Right? Every material has its own thermal conductivity. And that determines what type of conductor it is. Is it a good conductor, poor conductor, or in between, right? What's an in-between conductor called? Poor conductor. What? No. In between poor and insulator. In between good and insulator. Semi. Right? Semiconductor. There's more for electricity though. Right. So watch this here. Here we have a solid, right? And going through this solid is heat. Right, going through the solid is heat, right? This is the heat energy flowing through the solid. And what they look at is how the heat energy flowing per second. So we look at power, rate of heat flow. Rate of heat flow. What affects rate of heat flow? Anybody remember from what we just read? What affects rate of heat flow? Trying to read your lips. Say it louder now. What will control rate of heat flow? Will heat flow just like that? No, it must have a what? Must have a medium, okay. It must have a solid. And the solid must have a particular thickness, right? So let's see if we can write that here. Thickness, delta X. What else it must have? The obvious thing, believe me now. It must have something hot, or something cool. Must have a temperature gradient. So it must have a temperature here. Let's call that T1. And the next temperature here, T2. So there must be a temperature gradient. Remember, heat flows from high to low, right? So there must be a high temperature and a low temperature. Well, what else it will have? Well, we have to consider the area. So there's a cross-sectional area. And there's one more thing called the thermal conductivity and the symbol K. So all these things here control rate of heat flow. When they say rate of heat flow, is power on power, which is energy on time. Right? So right, before you go, Nathan, rate of heat flow, do you think it's directly related to the thickness? The thicker it is, the faster it will flow, the other way around. So the thinner it is, the faster the flow. So you will say the relationship is equal to proportional. All right, we will see that correct just now. What about the area? What do you think, Joseph? Directly related. We have big area. Will it flow faster? They're taken closely. Yeah. So you think directly. What about thermal conductivity, Sharon? What do you think about thermal conductivity? Remember, thermal conductivity, it was a good conductor or bad? Directly? Okay. What do you think about the temperature change, Emma? How do you think they're related? If you have a high temperature change, will it go faster? Yeah? All right. So directly. Anything left out we left out? Nope, yeah, everything. So let's see if we can create a little formula from this now. I want to just change this side. You can enjoy diagram. You're supposed to have the handout and print it. We don't have it as a just sketchy diagram. Sketchy diagram, put in all those letters. Right? So from this when you're done, we can kind of squeeze in the little formula there. So from that, we have this nice little formula. Right? We have rate of heat flow is equal to, I'm using the same things that you all told me, right? Area by temperature change all over thickness. Right? And then I'm going to include constant T. Right? One thing missing there is a sign. Yeah. Yeah, theta 1. Theta 1. Right? Quick question. Why did I squeeze in a minus there? Is heat being gained or lost? Lost, right? So the heat that you have here being lost as it goes through there. Right? Because here to be higher, here to be lower. So therefore, it will have a little minus sign. The minus sign just indicates that power is being lost. Alright? So you don't have to leave it in the calculation, something. You will see some solution with output. Let's put the kid out on this man, that's all. Like it's tough again. Smile at that. Alright, so this is the formula for rate of heat flow through a cell. Alright, and I kind of give you an idea how to remember it, right? You don't have to write the proportional things, but draw the diagram and the formula in the box. And when you finish, use a little math skills and tell me what's the SI unit of T? What's the SI unit of thermal conductivity? Right, Adam? I want to find the SI unit. Work it out, right? Chance if you can work out the SI unit. Heat. Remember, you have power there, you have area, you have temperature, and you have use temperature in Kelvin. Temperature in Kelvin, right? You have temperature and you have like. See if you can work out the SI unit for heat. Huh? What's oh, it's a work it out. Yeah, how much? What dimension analysis? Right, to hopefully recognize power is in watts. K is in we don't know. So I just put in like what X. Area is in what? Area is meter squared. Temperature change in what? Kelvin. And thickness is in what? What thickness is our meter? So do a little simplification and then make X the subject. And you should see exactly what Adam just read. Watts per meter per Kelvin. Right? Oh, very good. Watts per meter per Kelvin. Right? So we know what K is. K is thermal conductivity. We know what A and so on, right? But this here is a next quantity that we need to learn as well. There's a next quantity in here that we need to learn about. Right? You see that temperature change over delta X? That is called temperature gradient. And the only way that heat will flow is if that temperature gradient exists. So you see this delta T term delta X, we call that temperature gradient. right? And as I said, the only way heat will flow is if a temperature gradient exists. All right? So just make a note of these, delta theta and delta x, call that temperature gradient. And the only way heat will flow is if a temperature gradient exists. What would happen if there's a high temperature gradient? What would the rate of heat flow be? High or low? High. Right? So it will be high. What would you say? 3. Two laps. Like that's normally be slightly harder. We spend a lot more time on that flow. All right, next, taking this off, right? Right, let's run through the small note here. Consider a thin disk of some material of cross-sectional area A and thickness delta x. Suppose that the hotter piece is maintained at temperature theta, and the other piece is at that should be theta 1 and 2, right? Delta theta, and also the rate of flow is given by dq dt. So instead of writing dq dt, you can just put the power, right? It can be shown that if there are no heat losses from the sides, and at steady state, the following conditions will prevail. The rate of heat flow is proportional to temperature gradient. We talked about that already. And you have this nice little formula here, right? As I said, you don't have to worry with this differential part. That's just the show rate, right? What you have to focus on is that know that that is power. This is the thermal conductivity, area, temperature gradient. All right. Now, let's see if we can pick up a few more things in there, right? K is called thermal coefficient of thermal conductivity of a material, and it depends mainly on the material itself. So, for example, metal compared to like paper will have two different K values. Which one higher? The one for metal, right? The coefficient of thermal conductivity of a material is the rate of flow of heat per unit area per unit temperature gradient when the heat flow is at right angles to the faces, right? That's the thing we talk about, and this is the SI unit, right? But when they talk about steady state, they mean that the temperature at all points is the same, right? So now we wanna dive a little further into the temperature gradient. All right, so before we nothing that happens here, I don't want to give you the answer here, right? But let's dive a little further into temperature gradient, right? So here's how I do from again. We know that power is equal to Ke temperature delta theta on delta x, right? What I would like to know, if the rate of heat flow constant and heat constant, what's the relationship between temperature gradient and the heat? How are they related? So if you have a real good insulator with a low K value, what's the temperature gradient like? If you have something with a high K value, like a metal, what's the temperature gradient like? Temperature gradient means this, right? Temperature gradient means that the temperature here to the temperature here, same thickness, right? The temperature gradient means the temperature difference here is much larger. So if something has a high temperature gradient and the thickness is the same, then here will be high and here is low, right? Because the gradient is much larger, right? But if something has a small temperature gradient, temperature here and temperature here kind of close, right? So my question to you is, if I give you a solid and like metal and a piece of wood, same length, same thickness, everything, which one do you expect to have a higher temperature gradient? So you're saying that the higher the thermal conductivity, the smaller temperature gradient? Why is it? But sound nice. A lot easier explanation. Think about it. Think about that piece of wood, right? And you heat this piece of wood here, right? You heat a piece of wood, and the temperature here reach about 80, right? It's a poor conductor. What do you expect here? Some close to 80, something far from 80. What do you expect? So you know, heat a piece of wood. You heat a piece of wood, right? And if here is 80, here will be less, right? That temperature gradient will be high. So it appears that poor conductors will have a high temperature gradient, while good conductors will have a what? A small temperature gradient because a good conductor. So if you heat up here, that heat going to transfer here. So the temperature is going to be very close to the higher one. Right? So what does that mean? How do we relate it? Directly or inversely? Inversely. Right? So it means that temperature gradient is inversely related to thermal conductivity. Right? Then you note, but it's nice to write it down as well, in case you'll never open that hand up. Let's have one. I don't like to see long notes either. I like to see them short. Give me a little chat, I guess. Right? Right, thermal conductivity. Sorry. Right, temperature gradient is inversely related to thermal conductivity. Right, but you're on some logic why, right? Online, are you okay with reason why? Nancy? Here's my challenge to you. I want you to draw a graph for me. Just a line you have to draw. Just a line you have to draw. On this graph, this is a graph of temperature versus thickness. I want you to draw a graph of two lines. One line for K1 and one line for K2. Right? Draw a line for K1 and draw a line for K2. All right, online. So I wanted for a temperature versus thickness graph. I want you to draw a line that you think will represent K1. K1 is more than K2. Draw a line that will represent K1 and one that will represent K2 on the same graph. Think of what we just learned, right? We just said that temperature gradient is inversely related to K. Try that fast. I remember we start that lesson first Saturday in January, right? Not when school open. Right? I'm missing one class in January and 7th January. That's talking about the 3rd of January. Because I'm missing 170. Yeah, 70 here you have to do.
Even New Year's is Friday, Saturday, people
Friday, you do not. That's not what you want. Sometimes there's like a rush long thing. Right, so draw a line to K and draw a line for K2. Right, actually, I will draw two lines and you label which one is what. Label which one is K1 and which one is K2. Label which one is K1 out of the line, both are lines. Both are straight lines.
was good street lines.
Yeah.
I just like in English now. Not English.
You can show inverted curve, but my two lines are straight. I assume it would have been hallucinating. No, it has curve was like it didn't use the heat. So I assume it had no heat being lost. Curves mean dilute the heat. In real life, that's what it might be. So my question is, which is K1, which is K2? Look at the gradient. Just look at the gradient. Who has a bigger gradient? Broken line or the solid line? Who has a bigger gradient? This one, right? The one that slope more. No slope, less slope, plenty slope. Right? No slope is a horizontal line. So it means that K1 is a better conductor than K2. So this one is a good conductor. Well, I don't know if it's good, but better. And it's a poor, right? So I'm using these two words, good and poor. K1 is a good conductor. So this should have the lower temperature gradient. K2 is a poor conductor. So it should have a higher temperature gradient. Right? So your graphs will look like that. Right? Let's run to the small note now. Temperature gradient is a measure of the rate at which the temperature changes the most rapidly around a particular location. If the heat is flowing in a positive direction, high to low, then the temperature gradient is negative. It is the presence of a temperature gradient that causes the flow of heat. If the temperature on either side of the gradients are not maintained, then the heat flow increase temperature of the cooler side, thereby reducing the gradient. So we talk about it. All that's saying there, if it's a good conductor, the heat will flow so fast that the temperature gradient becomes smaller. Right? If it's a good conductor. The temperature gradient is the same at all points along a perfectly lag. Perfectly lag means insulated. Like if you're insulated, no heat being lost to the environment. So you have nice straight lines, right? So the temperature gradient is the same at all points along a perfectly lagged uniform path, while an unlagged bar, the temperature gradient decreases. So here you have lagged, here unlagged. Right? Here lagged and unlagged. All right? Then from this here, if we transpose the temperature gradient we will see that temperature gradient and thermal conductivity are inversely related. Right, so I'll show it to you mathematically, and I explain to you as well, right? This implies that large thermal conductivities gives temperature gradient that's small, right? The dotted line, poor conductor, solid line, good conductor. All right? No calculations as yet until now. Right? Now we're going to look at some calculations in this. Actually, let me just give you one thing. Try this now. Try this example. Example 1. Calculate the rate of heat flow. Calculate the rate of heat flow through a rod that is 50 centimeters long. Calculate the rate of heat flow through a rod that is 50 centimeters long with cross-sectional area 2 by 10 to the minus 4 meters squared with cross-sectional area 2 by 10 to the minus 4 meters squared and maintaining a temperature difference of maintaining a temperature difference of 100 degrees Celsius and 20 degrees Celsius. That's a question, right? Do you have to convert to Kelvin to find the temperature change in Kelvin? No, right? Because the same temperature change in Kelvin is the same temperature change in degrees, right? So you don't have to convert to Kelvin to get a temperature change. All right. 100 degrees Celsius and 20 degrees Celsius. So you don't need to convert to Kelvin, right? You can just minus it. Full stop. Note that the thermal conductivity. Note that the thermal conductivity is 200 watts per meter per Kelvin. 200 watts per meter per Kelvin. Watts per meter per Kelvin. Try that here. Work in the right SI units, sir.
Yeah, I what's up?
Well, you know,
We can come good one, but I was making you right.
I can move properly.
Now,
It's probably.
yeah, the guy is.
I was too cool, right? I get away and then I go ask for it.
You can see, but that's what
And I have a ask for it. That's enough.
the data begins.
Huh?
The data,
I see take a walk. I like what I can jump for now.
they only did time, yeah, come on.
Yeah. Find what
Still you're playing. Yes.
So we're trying to get warm outside of
Sure.
Right, you don't have to put the minus sign, just indicate power loss, right? What thickness again? What? 56.
50. 50.
Right, yeah, you can convert to meters. So you convert to meters, right?
So I get 6.4 plus minus
6.4. 6.41. Are you get that? 6.4. So just to give you an idea how to go through the formula, right? Right, but how these calculations really come, if you look at the note, I'll take it off there, right? But if you look at the note, there's something called a composite wall. Any questions here? Right, so all it will give you is different variations of this, right? But I want to build you up into one more concept before we start doing full calculation. Right, so if you look here, we have something called a composite wall. Right, we kind of have it here. So this wall has two main things. It has like mortar in front and then blocks in the middle, then air as well. So this wall is made up of more than one material, right? And because of that, it kind of controls conductivity. Like for those who went and tried to knock on the walls away, you reckon I can not sell that as I was. Because they need to handle bigger temperature changes than us, right? So they need to handle when it cool, stay warm inside, and when it's hot, the other way around, right? So what they have is something called composite walls. Walls of different thermal conductivities. So you might have a wall K1 and the next piece K2, right? And of course, it's the same concept. We need to see how heat flowing from here to here, right? We will still have an area. We will still have a thickness of each one. Let's call this X1, next one X2. There'll be a temperature change 1, temperature change 2. All right. So we need to figure out, okay, how am I going to find the rate of heat flow? I know that rate of heat flow is K by A by temperature change on X, right? I can easily find A. I can find the thickness. I can find temperature change. Problem is K. I have two different K values, right? So in a composite wall, we have materials of different thermal conductivity, right? How are we going to use this formula? How are we going to find this? The only way we can do that is if we have one K value, right? So we need to find a way to get one K value, all right? The little proof in the notebook, but here's what we need. Let's say, same thing. Let's say K1 is a better conductor than K2, right? K1 is a better conductor than K2. But I would like to replace K2 with K1. So I only want to have K1, right? I only want to have K1. Right? My question is, do I replace, when I take off K2 and I replace K2 with K1, do I need more of K1 to replace this or less? Right? So let me make it a little bit simpler, right? Let's say this is copper and let's say this is wood. When I remove this wood, do I need to replace this wood with more copper or less copper? Right? So I have my usual copper here and I want to know how much copper to put here. Do I need to put more copper or less copper to replace this wood? Bear in mind that wood is a bad conductor. And everything must stay the same, right? The rate of heat flow must stay the same. The temperature change must stay the same. Right? It wouldn't be the same thickness, right? That'll change. What do you think? Think about it. Yeah, you have a poor conductor. The rate of heat flow there, what? It's not a good conductor, so it's kind of slow, right? A real good conductor, the heat will fly through there. Right? So here's one way to figure out data. When I take off this wood, we'll work out the actual number later on. When I take off this wood and I want to replace it with copper, do I need more wood? Sorry, do I need more copper or less copper to replace it? I want the heat to flow the same way. So pretend it's taking 10 seconds to flow through here. When I put copper, it must still take 10 seconds to flow through it. So do I need to put more copper or less copper? More copper? Why? Number why? So remember, you have to take 10 seconds. So imagine you put a little bit of copper. Will it go through less than 10 seconds or more than 10 seconds? That's a good conductor, right? So what I need is more copper. I got this back. Right? I need more copper. Now, George, I guess it's first time. So I need more copper. Right? So what that means is that when I take off wood, I have to put more copper. Because think about it. It's a poor conductor. So the heat taking 10 seconds to flow through here. Right? So this have to take 10 seconds as well, but remember this is a good conductor. So when the heat starts to flow through here, it will flow through much faster. So I need more copper to replace the wood. That makes sense, Joseph? No? You sure? Or are you so now? You sure? So you need more of the good conductor to replace the bad conductor. Right? What about if I wanted to replace copper? If I wanted to remove copper and put all wood, do I put more wood or less wood? Less wood. Because of poor conductor. All right? How do we do this calculation? Well, there's a real nice relationship. K1 on X1 is equal to K2 on X2. Right? This comes from merging these two formulas, right? I'll show you that's now in the handout. But this formula can help me find X2 if I know K1 on X1. So I want to put some numbers into this now to see if it makes sense. right? Let's say it was equal initially. Let's say this was 10 centimeters, 10 centimeters. Let's say Q2 is equal to K2 is a bad conductor, right? So K2 is half a K1. All right? So K1 is a better conductor than K2, and K2 is half a K1. Let's try it here. How much copper do I need to replace wood? Everybody okay with that? How much copper I need? Right? So I want to replace wood, right? Wood is a bad conductor. So I want to replace wood. So wood is K2 over 10 centimeters. And I want to figure out how much K1 I need. Are you with me? Yeah. So I don't want, I know that K2, I know that K2 is half a K1. Are you okay? When I simplify this, this will flip up here. So I'll get K1 of 20. Cross multiply, I will get X K1 is equal to 20 K1. K1 will cancel, X is 20 cent. So it means I need 20 centimeters of copper to replace 10 centimeters of wood. And it makes sense because I need more to replace for a conductor. So I have K1 here. This is 20 centimeters. This is 10 centimeters. So now I have one area, one temperature change, one thickness, one K1. Now I can apply it here. Are you okay how to use this? Whatever you want to remove, put it here. Whatever you want to find, put it here. Right? Whatever you want to remove, put it here. Whatever you want to replace it with, put it here. All right? But you'll understand the concepts. If I have a poor conductor and I want to replace it with a good conductor, I need more. If I have a good conductor and I want to put a bad conductor, I need less. All right? Follow the notations. Copy this one. I give you one in the handout. I gave you one in the handout as well. Copy this one. You want paper now? Tell me how much wood is needed to replace the copper. I gave you how much copper needed to replace wood.
Yeah, right. Stop. Agent 99. Single business. Yeah, I haven't.
Muchas gracias. You have to find out how much wood is needed to replace the copper. How much wood will replace 10 centimeters of copper? Okay, that's good. Yeah. Is 10 centimeters of wood with 20 centimeters. Yeah, sure. We'll have access to more, but it's slower than us. Right? So in this last one here, we said that 20 centimeters of copper replace 10 centimeters of wood. So now I want to know how much wood is used to replace 10 centimeters of copper. So I know the formula I have to use. Right? I know K1 in this case, I want to replace or remove. Let me use the word remove, right? I want to remove copper. Copper is K1, thickness is 10. So I want to remove that. But I want to replace it with wood, which is K1 on 2, and I want to find X. All right? So you can string up the X there. You will get K1 on 10 is K1 on 2X. You can cross multiply, or you might recognize that these will cancel, right? So 1 by 2X, 1 by 10. X is equal to 5. Right? But you can kind of figure it out for yourself, right? Okay. So now we're going to put this together in a full question now. Right? So once we have the values, we can easily use the formula now because we have everything that we need. 1 K value, 1 thickness, 1 temperature change, 1 area. All right. The same question came about 3 times, huh? The one I got there. Oh. Era várias partes da minha experiência. Vou tá, vai na limpação. Só, tá tudo passando por o se eu já fui bom com a mas e quatro. Na vai para mim se eu tá eu quero ir right. I was I mean, I like you say I got a job. I saw appearance. I stopped at about very long after I think I got to take us right back. That's a good section of yourself. We don't know far, I know what to take track of it. Track of really. I guess the body hills and perfect water. That was seamless. And I like to say.
So speciality is
Yeah, I'm talking with talking. Yes. Kaya din ah. Right? This one is what? Brick, foam, brick. Same concept. Right? Instead of two materials, well, they have three spaces, but two materials, right? So they have brick, and then they have foam, and then they have brick again. All right? You have to do number one, sketch a graph of temperature with thickness. That's like what we did earlier. The difference here is 3 parts, right? So see if you can do this, please. Please try and include your values, -5, 50, and they gave you some thickness, right? Remember, you have three parts to this, huh? You have to calculate power at the end. Well, I hit so many parts, I'm gonna go on. Yeah. Right, the last part is determining the rate at which the heat energy will pass. Right, per square meter, I think important, each square meter. Right, sketch a graph, find the thermal conductivity of to remove foam, I think. The way to remove foam and use brick alone.
That's it. Yeah, building walk in and out. That's our. Okay.
Yeah, so we bring it everybody to do labs at once. So we have kids on the outside.
Yeah, but.
Huh? Again, of course. They're gonna break it. We're gonna break.
Fortunate.
Right, go to the third part of the graph confused, yeah? Do the first two and then figure out the third part. Look at that bar as well. And that bar is underneath. If you want, you can read part two. But yes, probably 4 come down. Right, if you read part two, you will see the actual values. I don't know how to show all of that. Take off. Must be right. First one I drew just right now. Now you have 10, 5, and 10. You have to show the ratios and so on. There's some nice ones too.
So we're going by state level.
Huh?
We're going by state level.
Very what? Like right. I go in, my neck.
Yeah, go with it.
If my bed, so go.
And then we pass it. Yeah, we pass it.
Oh. Anyway, but I had a good market.
So you play mass example.
And after I don't.
How do you mean? I'm not all our costs.
You know where customers are made, you know where console.
What is that?
That's all is good. By the time this guy have reached on the way somewhere in pushing. That's why I like that. Ramang Uta Uga. Right, you have to draw a graph accurately because they give you thicknesses and they give you temperature. After the value, higher. Well. Yeah, the values. Yeah, yeah, it's got a graph and it must have all the values. So. Yeah. That's. Maybe now we sort of but it will from high to we start at 6 and 4 to 9. That's fine. Right, so start at 30, right? What you can say about these two gradients? Right, so just checking the graphs out. Everybody thinks that you need, right? So checking the graphs out, right? So it might look that it should start at -5, but heat wouldn't flow from here. Okay? Heat will flow from 30 to -5. Right? These two gradients here. What you can say about these two gradients? Constant or the same? Same, right? These two are the same, and which has the higher gradient? Form of it. That's a gradient.
It will go.
Oh, shucks, I think the wrong thing in my head. Yes, correct. Right? So you have to make sure, try to make sure that, right, you have these two being the same.
So you penalize if you don't draw your two break variance. See?
They had to be close to the same. That is a little off, it's okay. Right? Because it's a sketch. Right? But try to make sure that these two are the same, right? Right? Good conductor, smaller gradient, this is larger gradient, right? It should actually be a little sharper than that, yeah, but okay with that? Try part 2 and part 3. I wrote the values down for you, right? So this is the part question.
I get the idea.
Right? So you want to remove 5 centimeters of home brick. What is the area for? Part 2. And when you don't need that,
Also, calculating 3% would. Will I see?
Right. Right, quick, yeah, 5 minutes.
No, it's about two. Haven't, yeah. We most of what we did. Or, just. It's the game. Yes. Now, it's. Go back. Yeah, like some instance. I lost your last name. Right. For access, the access to any place. Like, when it is we have no exams, so the way yeah, we get exams. Right. So. Yeah. It's online. It'll be so good. So many people want to go to say for both of them. I don't know. There's the yes. I feel like I'm up with.
So here, I want to replace foam, right? So I want to remove foam. So the first thing I write is the formula K1x1 is equal to K2x2, right? K1x1, I want to remove foam. Foam is 0.016. And X1, how much foam we had? 5 centimeters. And I want to replace it with brick. Brick is 0.48 divided by X. Right? Cross multiply and solve for X. You will get 5 by 0.48 divided by. Do you expect more or less? Do you expect more or less? Good conductor, you place in a bad conductor, so you should expect more. How much is that? How much? 115?
150.
150? 150? Yeah? 150 centimeters. Did you get that right? Everybody get up? 150. Next, power. We know that P is equal to KA delta theta on delta X. So now we have all what? All what? All brick, right? So we have all brick. So now K is 0.48. What's the area we're using? Question said per meter squared. So you're using 1. Right? What will be the temperature change? What is temperature change? We're going from 30 to minus 5. So that's 30 minus 5. All over thickness. What's the overall thickness? 10 centimeters, right? So it will be 10 centimeters plus 150 plus 10. So I have 1.7. Y'all follow why is this? Right? 10 initially. I replace with 150 and I have 10 again. Right? 10, 150, 10. How much is that? 9.9. Well, yeah, I say you know always have to put in mind. Fine, that's what? 9.9?
Yeah.
Let's try one more. That was brick, right? Next one, I think it's good. All right, do my favor now.
Sure.
Pick up it now. Okay, that's good.
This one.
Right, and that's when we're gonna on the question part. That's now, I'll go back there. Right, that's the question, right? Same thing, they're asking the same thing. And then I'll go back up, right? That's a good question then.
So you always about.
Adding and dividing.
Oh, yeah.
How much brick they have right now, right? But can that replace the foam? With how much brick? Yeah, 150, work it out.
You what were you?
Because 150 plus 20 is,
70.
then it converts to meters.
Oh.
Try this next one, same concept, right? Same concept, plywood, foam, plywood. This one should be easier. What?
Yes.
What is it? Yeah.
That's it. When it says, when it states it as being said,
Like you already up.
Yeah.
What's that again? Two.
So, so, well, the alternative pretty 70. So the latest one, I do. I have to over. So I can really get like about 500 like there's like good, good coach.
And just like,
Yeah, but so I can,
I think I.
it bigger, yeah. If I don't know, I have stage, I'm not done yet. If I'm done.
I think last time we went with the pool and that was 50. I didn't check this. Password is next. I looked into like those people try it out. Anybody is good. Yeah. Somebody said not the most I let it die.
Yeah, not it, it was very well, I think 6 of them.
Don't forget that my body.
Say yes, yeah, I said.
Now I try it.
If you buy good stuff.
No, I will black market something. I never
Yeah,
black
was not with price much.
I nice.
You can sell that too.
Profit. Like you get a 16 for 500, a 60 plus 545. Yeah. 545. Yeah, folks. 16 Pro Max.
So it is online. It is, let's say, this is if this is 60 months, like 1.5 years, you get up to 670 years.
On the 15 Pro Max.
On the organization, when you buy it for 70 per, but how do you last year? What you get 670. So you have to be 400 euros, put it in the world. So then you get for that half the price of that's when you put it on the show. So it's really much.
I know brand new gun, but I get it for. I don't want to pay more than 16 dollars.
And same thing, yeah, these 70.
I don't get yeah.
Yeah.
Yes, I say in my but no friend goes man.
Yeah.
That go on, but huh? No, that's fine. That was quite loud. But right, plywood, foam, right? All right, done. What the graph be the same? Same shape? Plywood and plywood is good conductors and foam is. The only problem is that they are all 1 centimeter thick. So you have to make sure they're the same thickness. So the graph shape will be the same.
So if you go down plywood, simple.
Huh?
If you go down plywood, you will see. Yeah. But plywood more plywood like. What is that?
I know, but compared to foam, it's a better conductor. Remember, it's compared to foam. Y'all done? I got number in it and why is the same thing, different numbers. Last one are we done, right? Can be like Keshav, I showed Keshav doing you over there. Watch. He does sending heart already.
Stop.
Can be like Keshav now.
So you can catch them last shot with two of this. Yeah, and you put them to I really. Hey,
Where do you be on this? Save it. Save it.
therefore,
What's the J-phone?
you can. Something when you brought this in mind, right? Okay, I think so.
No, it's fine. No. I want to save us. Then prove all over.
Thank you, nobody touch it. Yeah.
What do you call it?
Yeah, it's a couple of us.
Come here, you can dance.
Yeah.
That one right something.
Yeah, it's
I'll get to the first part, right? You have something like that. Right? Part two, what are we replacing? We're replacing 1 centimeter of foam. Foam is 0.012, and we're replacing it with 0.24 plywood. Cross multiply, x is equal to 0.24 over 0.012. How much you all got? 20. 20 cm. Nice. So find the equivalent. I think they gave you area somewhere, right? They gave you area down there. So power is equal to K value we're using is what? All plywood, right? 0.24. What's the area again? Right, 0.6 by 0.4, nice. Temperature change is 28, and the thickness is how much? 122, 0.222, right? Yeah, 0.22. So the power is how much? 7 minus 7.331. Right? So that's the way you handle questions like this. All right, so that's it online. Copy it down. Hope you all got the same values. Anybody confused online? All right, so that's it. You have to log out.